Hi everyone, welcome to my presentation of our paper titled A Novel Probabilistic V2X Data Fusion Framework for Cooperative Perception. My name is Mao Shan from the Australian Centre for Field Robotics, the University of Sydney, Australia. In this presentation, I will first talk about the introduction and related work. Then I will present the details of the connected platforms we developed at ACFR. I will then focus on the probabilistic V2X data fusion framework proposed in this paper, followed by the testing results obtained from simulations and real-world experiments using the real connected platforms. Lastly, the presentation will close with a brief summary. I'd like to kick off the presentation with these two videos, where you can see the autonomous vehicle from our research group operating near the iconic Mako Django building in the University of Sydney campus. I think all of us are quite excited about the coming of autonomous driving technology. To make it happen, an autonomous car is usually equipped with a suite of onboard sensors like a multi-beam lidar, radar, and a set of cameras to perceive the traffic environment so that it can plan a path and navigate around without hitting anything or anyone. These purple blobs in the video represent the objects the vehicle is detecting, yet these perception sensors have their limitations like field of view and detection range. Also, it may have misdetections and false detections due to different reasons. More importantly, most of these sensors are line-of-sight sensors, so an autonomous vehicle couldn't do much about visual occlusion that is everywhere in a traffic scene caused by buildings, trees, and other road users. Failure to detect an object, for example, a vulnerable road user, can often lead to catastrophic consequences. This is a situation where the CP, which stands for Cooperative Perception, can help. This picture shows a simple setup of CP where an intelligent roadside unit is deployed at this intersection to sense and monitor the intersection. There's a connected vehicle here about to turn left. With the V2X objects received from the roadside unit, the CV becomes aware of what's going on behind the building before turning. Now we level up the complexity by adding another CV that has sensors to perceive the traffic at the same intersection. In this case, the same CV can receive the V2X perception information from both the IRSU and the other CV, and it can perform fusion of the perception to produce more reliable and accurate perception results. From the pictures, we can see that there are a few attractive advantages of CP. First of all, CP can extend the horizon of a CV with the V2X perception information received from other connected ITS stations. The second advantage is that a CV can improve its perception quality by fusing its sensory data and that from other connected ITS stations. Lastly, the explicit digital representation of road users and other objects can help with traffic monitoring and management for improving traffic safety and efficiency. This is a demonstration we conducted in a real urban traffic environment, which is set up following the simple case of the CV we talked about in the previous slide. A CV was driven from the side road here to the main road. Later you will see it made a right turn to another alleyway where the visibility for the turning was very poor due to the occlusion caused by a corner building. There was an IRSU deployed here to monitor the traffic at the intersection of the main road and alleyway. As you can see, before the vehicle turned into the main road, it's already receiving the perception information from the IRSU and knowing what's happening on the main road. When the vehicle was approaching the alleyway, there was a hidden pedestrian behind this building, but couldn't be seen by the driver and the vehicle sensors due to occlusion. However, thanks to the IRSU and CP, the vehicle received this critical information seconds before the hidden pedestrian can be visually picked up from the vehicle's perspective. This shows that the vehicle can see around the corners using CP so that it can consider this safety crucial information in its decision making. Now let's roll back to the fundamentals about V2X. V2X stands for vehicle to everything, including vehicle to vehicle, vehicle to infrastructure, vehicle to pedestrian, vehicle to network, etc. It enables a CV to share essential information with other connected road users in the traffic scene. This emerging and promising technology has enormous potential for improving efficiency and safety of road transportation. There are mainly two popular V2X standard message families in the world, one in Europe and the other in the US. The CPM, the Collective Perception Message, which is specifically designed for CP, is a recent member of the ITSC G5 message standardized by ITSC, European Telecommunications Standard Institute. On the US side, there's early-stage standardization work in SAE, Advanced Application Technical Committee, to standardize messages and protocols for sensor data sharing in SAE J3224. Now we can take a quick look at the related work. CP is not a new concept. There's early work that shares raw sensory data, which is quickly proven to be infeasible due to the extremely high communication bandwidth requirement and poor scalability. Then researchers turned their attention to sharing abstract representations of perceived objects. There have been proposals of different messages for CP in the literature. The standardization of ITSC-specified CPM started in 2019. Using standard message in a V2X communication is important to make sure interoperability between platforms of different types and from different manufacturers. There are also papers addressing the CPM generation roles, striking a balance between CP service quality and the V2X network resources, and aiming at avoiding redundant data transmission and communication congestion. For V2X data fusion approaches for CP, most of existing methods assume perceived objects received from other ITS stations to be independent object observations. For the convenience of ignoring estimate dependency in the fusion, there's also work that perform deterministic association of local and V2X objects, and a work that separately processes local sensor data and V2X data. There's also non-parametric V2X data fusion methods based on occupancy grade. They are known to be computationally expensive. There's also an interesting paper in 2019 that proposes a check-to-check fusion method using a covariance intersection for KOPEOG CPM. However, the method is only evaluated in a numerical simulation with 2 CVs. Lastly, there are many other papers exploring the use cases and the benefits of CP and the papers that tackle the challenges. Due to the time constraint, I wouldn't go through each of them. Interested audience can refer to these papers listed here. So there are 2 main contributions of this paper. The first one is the proposal of a novel probabilistic V2X data fusion framework for CP. It supports joint fusion of different types of perception information, including the host vehicle's local perception data, V2X independent object observations, and object checks received from other ITS stations. It can perform safe and consistent fusion of the perception data from multiple sources without worrying about any cross-correlation. The validation of the method is conducted through results from numerical simulation, Carla simulator, and a real-world experiment using real connected platforms. The other part of the contribution is a demonstration of how the CAV considers the fused V2X information in its operation, and also the critical role of CP for the safety of CAV operation. The following 2 slides introduce the connected intelligent platforms we built at ACFR. We have built 2 intelligent roadside unit prototypes. The first one is equipped with a 16-beam lidar and multiple cameras, and a workstation for real-time data processing. The IRSU also encodes the perceived objects into ITSC CPMs and broadcasts the messages out through Coda Wireless MK5 IRSU. Later, we built a lightweight and more portable version, Prototype B, which only has an RGBD camera as the main sensor and a single-board computer for data processing. It has a small form factor and is battery-powered. As for the vehicle platform, we use these 2 electric vehicles that have been retrofitted with a suite of perception sensors, including a multi-beam lidar and 6 cameras. The vehicle can achieve full autonomy in a campus environment. Now with the add-on of Coda Wireless MK5 OBU, this autonomous vehicle is turned into a CAV, connected and automated vehicle. I would like to spend a little time on presenting an overview of the proposed V2X data fusion framework. When CPMs are received and decoded, the V2X perception information contained in the message is registered in the sender's coordinate system. So it has to be transformed into the receiver vehicle's local coordinate system before it can be fused into its perception pipeline. Following the coordinate transformation, the V2X perception information is fused into the fusion center within the receiver vehicle. The V2X perception data can be object observations or object checks, so the fusion depends on the information types. For received V2X object observations, denoted as ZR, it's safe to use common update or other traditional Bayesian filters to perform the fusion. This is primarily the same to local perception data denoted as ZL here. But the fusion of received V2X object checks requires extra care, because we don't know how much the V2X object checks are correlated with any prior information. This brings the risk of double counting of information, which leads to over-optimistic estimation results. To solve this, we propose to use covariance intersection when performing check-to-check fusion for received V2X object checks, denoted as tau R in the figure, without knowing the cross-correlation. We also adopt a probabilistic association of local checks and the remote checks if they are received for the first time. Lastly, the updated object checks as a result of the joint fusion, denoted as tau L plus, are then encoded into ITSC CPMs and transmitted to other ITS stations through V2X communication. Due to the time constraint, I will skip the numerical simulation results. I will now present the validation results from the Carla simulator. The simulation participants include 2 CVs and 3 pedestrians. The 2 vehicles approached the same intersection from different directions, and both made a right turn at the intersection. Both vehicles were equipped with a multi-beam lidar and front-facing camera for pedestrian detection and tracking. They were also exchanging the object checks through ITSC CPMs and performing V2X data fusion. As the video shows, the number of pedestrians each vehicle could directly detect varied at different times, but through V2X data fusion, the CAF1 managed to continuously track the 2 walkers in its local coordinate system, as shown here, even though it couldn't detect them directly using its onboard sensors. To quantify the uncertainty of pedestrian estimate result, we use the trace of the covariance matrix of the 2D positions plus the heading in the state estimate of each pedestrian. This figure shows the change of the pedestrian uncertainty over time. As mentioned before, at this time point, only the CAF2 could detect the walkers, as the blue and orange arrows indicate, but the CAF1 managed to track them through the V2X information from the CAF2. And the uncertainty kept dropping when the vehicles were moving closer to the intersection. It's also shown how the CAF can consider the V2X fusion result in its decision-making and improve safety. As the CAF1 speed figure shows, the CAF1 decided to slow down and give way to the crossing walkers. I need to stress that this happened before CAF1 could directly detect any of the walkers. Yet, CAF1 safely responded to the crossing behavior only based on the V2X perception data received from CAF2. Let's move on. At a later point, CAF1 could detect the first walker directly using its onboard sensors, as the blue arrow marks. This is why its tracking uncertainty dropped significantly. Later, at this time point, the other walker also could be directly detected by CAF1. Now, both walkers could be tracked by CAF1 accurately. The last part of the result comes from a demo conducted in a lab environment. The CAF was driving towards a designated pedestrian crossing, and an IRSU and another CV were deployed here to monitor the same crossing area. The CAF here did not use the internal perception capabilities in its automated operation to highlight the benefit of using the CP. The CAF in this case was receiving perception information from both the IRSU and the CV through V2X communication and performed data fusion to generate more accurate and reliable estimate of the pedestrian. The CAF, as you can see, slowed down and gave way to the crossing walker using the fused tracking result from the IRSU and the CV. It then continued to move after the crossing became clear. As you can see from these 2 pictures, before fusion, there were 2 pillars representing 2 pieces of perception information from the IRSU and the CV. They are then fused together to produce a single estimate with a smaller uncertainty. Now let's wrap up this presentation. In this paper, we propose a novel probabilistic V2X data fusion framework for CP. The simulations and real-world experiment results validate the proposed method and showcase the benefits of using CP for CAF operations in terms of improved perception quality and safe decision-making, particularly when it's interacting with vulnerable road users. For the future work, we would like to push our current CP work to the next level. We are looking at opportunities of deployment of the technology in public traffic environments and on-road trials. Also, we can explore augmenting the CPM with additional information, for example, future path, intention, learn features, which can trigger more future CITS applications. Thank you.